Okay, this problem is almost identical to example 5, except that we have a 30-60-90 right triangle. And notice I used the letter beta instead of the letter theta this time. Again, just to introduce you to more Greek letters. It doesn't make the problem any different. The letter you pick, just like if you pick X, Y, or Z, you know, it means the same thing. So in this case, beta is the angle I chose to call it. KL is 4. It says JKL is a 30-60-90 right triangle. And they want us to find the 6 trig ratios for angle J with measure beta. So we're dealing with beta. And I'm going to go that this is the 30, this is the 60, just because it looks like that. So beta is the 30-degree angle for the sake of this problem. All right. So if beta is 30 degrees, all right. Remember the right relationship of sides in a 30-60-90 right triangle is the 30 degree is the smallest side, 1. The 90-degree side is the biggest, so 2. And the 60-degree is the middle, which is square root of 3. 1, 2, square root of 3 are our numbers. And again, if we do just like before, 1x, square root of 3x, 2x. So I know that 1 times x equals 4, which means x equals 4. So 4 times the square root of 3 and 4 times 2 is 8 would be the other two sides. The side opposite 60 is going to be this, k is 60, so opposite JL. That's going to be my 4 times the square root of 3. And 90 is L, so this is side opposite. 90, 2 times x, so 2 times x is 8. So again, if you know the one side, you know 1x equals, right? You can very easily figure out what x is, and then you can figure out the rest of it. So just like that, we know all 3 sides of this. If I'm dealing with angle beta, I need to identify the opposite, the adjacent, the hypotenuse. So beta is here, go across, that's the opposite. Angle L is the right angle, go across, that's the hypotenuse. And the third side must be the adjacent. So now we know all 3 measures, what they are. We're going to look at SOHCAHTOA to establish the sine, cosine, and tangent. And then use those reciprocal functions, cosecant, secant, and cotangent, to find the values of those. So, sine of beta equals fraction. Cosine of beta equals fraction. Tangent of beta equals fraction. Cosecant of beta equals fraction. Secant of beta equals fraction. Cotangent of beta equals fraction. To draw a good beta, you start at the bottom of the tail, come up, and then around. That's how you make your betas. So down, up, and around.
Is that TOM or
This?
third one down?
TAN, tangent. There we go, right prettier. So, sine is opposite over hypotenuse by SOHCAHTOA. Opposite 4 over hypotenuse 8. That equals a half. Cosine is adjacent over hypotenuse. That's 4 times the square root of 3 over 8, which is the square root of 3 over 2. Notice when you deal with these radical, non-radical pieces, when you're looking at these objects, if the same, or I should say if the numbers outside reduce like normal numbers, you should reduce them. So 4 and 8 are both regular numbers. The square root of 3 is just kind of coming along for the ride. That makes 1/2. 1 times the square root of 3 is just the same as the square root of 3. Tangents opposite over adjacent, that's 4 over 4 times the square root of 3, which is 1 over the square root of 3. Now obviously I need to fix that, but I don't want to fix that until I make all my reciprocals. Alright, so everybody comfortable with what I got so far? Sine, cosine, and tangent based on SOHCAHTOA with the 3 side values that I know. So cosecant reciprocates sine, so 1/2 is sine, reciprocating at 2 over 1, better known as 2. Secant reciprocates cosine, so I'm going to flip that over, I'm going to get 2 over the square root of 3. That of course needs to be fixed, so I multiply top and bottom by the square root of 3. And that gets me, after I simplify, 2 times the square root of 3 on top, Square root of 3 times itself makes 3 on the bottom. Cotangent reciprocates tangent, so flip that over, I get the square root of 3 over 1, better known as the square root of 3. So, 1/2 simple, square root of 3 over 2 simple, 2 simple, 2 square root of 3 over 3 simple, square root of 3 simple, 1 over the square root of 3 needs to be fixed, so times the square root of 3 on top and bottom gets me the square root of 3 over 3. So all 6 trig functions simplify completely, no radicals left in the denominators. Again, if any sine, cosine, or tangent has a radical in the bottom, reciprocate to get your cosecant, secant, cotangent answer first, then go back and fix it afterwards. It's easier to reciprocate this than it is to reciprocate that. So if one of these is not fixed, get the answers over here first and then fix it. All right, just real quick, I kind of brushed through this part pretty quickly. I just want to make sure that everybody has a complete understanding of that bit there, so we can do this. This whole ratio technique, I haven't done this before, so I kind of threw it at you, and I kind of threw you right in the deep end right away. So let me just real quick just show you a couple of these, because again, that's going to be the key to these problems, is being able to get those missing sides. So let's start off with the 45, 45, 90 idea. 45, 45, 90. And let's just say that I know this is 10. All right? So my relationship of sides for 45, 45, 90 is 1, 1 square root of 2. So 1x, 1x, the square root of 2x. All right? So if we take a look at the side I know 10, and 10's opposite 90. So 90 is in the ratio of the square root of 2x. So this is what it looks like. The square root of 2x equals 10. The ratio idea equals the actual side measure. If you divide both sides by the square root of 2, that's what x equals. And just like other things, if I have a square root of 2 on the bottom, I'm going to multiply top and bottom by the square root of 2 to fix it. That gets me 10 times the square root of 2 over 2, so x equals 5 times the square root of 2. 1 times x, 1 times x, that's the other two sides. So 1 times 5 square root of 2, 1 times 5 square root of 2. So whichever side you know in the ratio, just take that piece equals that number and solve for x, then you know what x equals. All right? If I'm looking at a 30, 60, 90 right triangle, we'll say that's 30 and this is 60, and that of course is 90. And let's say that I know that this is 10. Let's say that, go with 10 again. All right? Again, our 30, 60, 90 relationship, 30 to 60 to 90 is 1x, 2x for 90, and the square root of 3x for 60, right? So once again, what do we know? We know 10, which is opposite the 90-degree angle, and the 90-degree angle in the ratio is 2x. So once again, I'm just going to write down what I see, which is the ratio object 2x equals the actual number 10. Divide both sides by 2, x equals 5. 1 times 5 is 5, that's opposite the 30-degree side. The square root of 3 times 5 equals 5 times the square root of 3, that's opposite the 60-degree side. So whichever side they give you, just let that ratio piece equal that actual measure to figure out what x is, and then just use the ratio to get all three sides. Works 100% of the time, it's pretty straightforward, pretty efficient. It's a good way to do those problems, all right? But again, we hadn't done it that way recently, or I don't know if we ever did it this way, but if you never did it that way, that's how you do it. So again, your ratio numbers you already know from doing it before with the proportions. Just stick an x on everything, and again, whichever side you know in relation to the angle, that's what that equals. Solve to get x, and then you got whatever each side is based on that relationship.